Hello, everyone. My name is Alon Greenberg Dana. I'm from the Department of Chemical Engineering at the Technion. First, thank you so much for the invitation, and especially thank you for James Michael for inviting me and doing all the organization. So thank you so much. I invite you in the following session to dive with me into the world of predictive chemical kinetics. And specifically, we'll see how agentic workflows and smart agents can assist us here in making predictions onto reactive chemical systems. So let's begin and diving in by first stating the overall goal of our research group or of this domain in science. The goal here of predictive chemical kinetics is to make predictions onto reactive chemical systems, meaning we know the temperature, the pressure, and the composition to begin with, and we are asking, how will this system behave? So a famous quote about models in general comes from John von Neumann, the famous mathematician from the previous century, who said, if you give me a model and 4 degrees of freedom that I can tweak however I want, I can fit an elephant. And if you give me the fifth one, well, I can fit his trunk. A tribute study, a tribute paper that was published in 2010 by Max Planck scientists towards John von Neumann actually did that. They took 4 complex numbers, and as you can see here, they drew an elephant. They took the fifth one and they, wiggled his trunk. In the spirit of John von Neumann, and also the paper here, we also say that we're not in the business of fitting elephants and fitting parameters. We're in the business of making predictions and high quality predictions for reactive systems. In this talk, I'll first show you the layer of what we call automation, the software that can generate these predictions. And then after we understand the keys, the keyboard, the buttons, we'll see the agents that can play with them. So let's start with chemical kinetics. The known problem, of course, is that the number of parameters that we need in order to make a prediction onto a reactive system and understand all the intermediates and the cross reactions, well, that number is simply much greater than what's available to us experimentally from what we can actually measure. We can't measure all rate coefficients. These could be hundreds of thousands of rate coefficients just for one model. Of course, we can't go to the lab and measure all of them. And here comes computational chemistry. We can use automated method. We can run on a server cluster, DFT and higher levels of theory and get automatically rate coefficients. So that's where computational chemistry comes into play. The first software tool that I'll introduce is called RMG, the Reaction Mechanism Generator. RMG was built and is still maintained and built by the Green Group at MIT. And I'll introduce RMG in a nutshell. So what does it do? RMG has some tasks. The first one is to tell us what are the significant intermediate species in the model that we care about. We don't need all of the nuances, but we need the major species, and the user can actually control what major and what significant is for their application. And also we need the reactions. And again, we just need the significant ones, the important ones. You can have niche reactions that won't affect your observable. You'll have to come up with a way to differentiate between those, of course, but you need the significant reactions to make predictions onto your system. And that's what RMG is set to do. We also need to quantitate everything to actually give numbers and rate coefficients. So we need all the rate coefficients in the system, not just the significant ones, because we have to make the distinction between what's significant and what's insignificant. We do that qualitatively and quantitatively, primarily based on rate coefficients. So how does RMG work and how does it achieve this goal of understanding and predicting the species, the reactions, and quantitating all that with thermodynamic properties and reaction rate coefficients? So let's see a short animation that shows how RMG thinks. In this animation, I'm giving RMG an initial compound, AIBN. That's the actual IUPAC name. I'm giving it concentration. RNG is great for gas phase. It also works very good for liquid phase reaction. So this is a liquid phase reaction. We have 50-50 by volume methanol water solvent. We are open to the atmosphere, so that means oxygen, nitrogen can diffuse in. And here's an intermediate temperature, low temperature, and we're waiting for 3 days for this experiment. So that's a real experiment that people make for polymers, for example, or more correctly, in the pharma sector for stress oxidizing a drug. So that's a radical initiator. Anyway, we don't really care about the chemistry here. We care about how RNG thinks. So this tool, RNG, that creates a model for you, thinks and divides the world into a core and an edge. So the core is everything that really matters, and the edge is everything it populates and still haven't decided whether they matter or not. So it starts by taking your initial mixture and just dumping it into the core. So here we have our main molecule that's going to react, AIBN. We have methanol and water, so here they are. We're open to the atmosphere, so there's nitrogen and oxygen, and there's pH, for example, so I can represent it with these two ions. And RNG can look at new molecules, so structures it has never seen exactly that way, and apply chemical rules. So it has more than 120 chemical reaction families, so templates it can apply, and it will take a new molecule, apply the template for it, and predict how it's going to react. So here's what RNG does. RNG is going to ask now 2 questions, and it's going to do that iteratively. Question number 1 is, so what's going to happen? What are the reactions that are possible in this new soup of molecules? So it applies its templates. Soon we'll see how it does that and where the data is coming from. And it predicts the possible products. And it also predicts the actual reactions, as we said, rate coefficients, the reaction family. So that's question number 1. What's possible? What can this mixture generate? Question number 2 is, all right, so what's significant out of the species that were generated in the edge? RNG will identify significant species primarily by how fast they are being created. There are additional criteria. For example, a species could be generated slowly but has a significant effect on a core species. So RNG will grab that as well. And RNG will continue iteratively. Each new species it suggests, it will ascribe thermodynamic properties for it. So delta G, delta H, delta S, heat capacity. Each new reaction, it will give it a rate coefficient if it's in gas phase, so a pressure-dependent rate coefficient as well as temperature where it matters. And here we have temperature-dependent kinetics for liquid phase. Eventually, RNG converges. The models are generally large. Here we see a relatively small model. RNG says if you want to know how this AIBN molecule decomposes for certain user selected tolerances, so you need about 30 chemical species, and that's the magic. RNG tells us which species. That's hard to know. And it gives us delta G's for them, so we can get equilibrium constants later on, or inside the simulation. That's for free, of course. And it also tells us which reactions are important. So we see here we need almost 100 reactions to describe this process. And the hard lifting here, the heavy lifting, is to know which reactions. So it gives us a list of exactly 94 reactions and telling us under these conditions, these are the significant reactions, and it also ascribes rate coefficients for them. Overall, RNG explored more than 200 species and 1,600 reactions, and again, that's a very small model. It ran in 2 hours, simulating a chemical time of 3 days. Usually, our models are much larger. So that's just an example of what RNG does, and as I said, the following natural question is, so where do the data come from? How do we generate it, and how does RNG know? So first, we don't invent the wheel. RMG uses existing libraries. So these are curated datasets from literature or from our own previous computations or from experiments. So we have these thermodynamic properties for known species and known rate coefficients. Then the power and the magic, the real power of RMG, comes from estimations. It can move quickly and on the fly estimate using, for example, group theory. It estimates thermodynamic properties. Using decision trees, it estimates kinetic rate coefficients. And using machine learning, it again improves the thermodynamic property predictions it has. So that's the real power of RMG, making predictions, making it relatively fast, and being able to provide a model, a skeletal model, at least at first, and then we enlarge it for the new system we would like to explore and study. That's great. As we said, it's very hard to do, and RMG does the heavy lifting. But since these are estimations, the problem is that it's not accurate. We're using group theory or decision trees. So really what we want to do next is improve the model, improve the estimations. And here we use ab initio methods, ab initio calculations, DFT, density functional theory, or wave function, which are more advanced methods like couple cluster or DLP no couple cluster. So we use these quantum chemical computations to improve the model. So now we have the skeleton, we know the mechanism, we know pretty much how it works, and now we can also improve it and make it more accurate. We do that iteratively. There's another tool, I won't have time to show it here. There's another tool that actually does that iteratively, generates the model with RMG, defines the species and the reactions that the thing we care about. We call that the observable. For example, we care about the concentration of the pollutants. So our tool will run sensitivity analysis and we'll see how to perturb all the input parameters and which one has the most significant effect over the observable we care about. Then we know that we have to nail that property down, that data down, and have low uncertainty. Otherwise, it will propagate, and that's what we do. We understand where the data came from. If we trust it, fine. If it was estimated, then automatically it's being sent to the computational software. So let's see the computational software. The tool we created and we maintain in our group at the Technion is called ARC, Automated Rate Calculator. So ARC will run the high-level ab initio thermokinetic computations. It's a documented tool, extensible code base that actually delivers from just strings, from smiles. It will give us the full thermochemistry of the species and reaction rate coefficients in gas phase or in liquid phase. So what does ARC do? ARC begins with a structure discovery, which means what's the lowest lying energy conformer for our species in 3D? So now we're going into the DFT and 3D domain. So ARC runs conformer generation and finds the lowest energy conformer. Then it performs the quantum mechanical calculations. It needs the 3D conformer to run the DFT, of course. ARC does that also for transition states. As we can see here, these reaction paths were computed by guessing the transition state, and ARC, the software, the ARC tool, has methods implemented in it, literature methods plus in-house methods, to come up with a transition state. So TS search, transition state search. ARC will do that. It will hypothesize how the transition state looks like in 3D, which is a hard problem and honestly not entirely solved in the chemical kinetics community, although we already have some good tools and some good results towards that, but still in progress. Overall, there are some hard reaction families that we're working towards solving them and automating them as well. And ARC will give us the transition state for the reactions we care about. Then it runs the quantum mechanical calculations. It can run it locally on the computer where you're running. It can run it on a remote server. It will SSH into the server. It can run it on a cloud. It can run on a server, run some computations on it, and some other computations by SSHing into another server. So Arc can really be very flexible, and it can work with many proprietary and open source software tools. So proprietary tools could be Gaussian and MolPro and QChem and TerraChem, all these tools for DFT and wave function, and also open source tools like Psi4, for example, to actually run the calculations. What makes Arc powerful and really automated is its ability to troubleshoot the computations. So by troubleshooting, we can really have an automated workflow, capturing errors, for example, technical errors if we need more memory for the computation. So Arc will identify a failed computation, it will rerun it again with more memory, but also troubleshooting scientific issues. If the integral didn't converge, if you need a specific keyword that an expert can provide, so Arc is programmed to provide that. Eventually, it runs statistical mechanics and processes and gives you rate coefficients and thermodynamic properties that you can then plug into RMG and in the loop generate a model. These are the basic tools. As I said, we have more software, we have more layers and more automation, but these tools are what I call the keyboard. Now we need someone to work with that keyboard, and you guessed right, it's both our students and our researchers, but also the AI agents that can work with these tools to generate predictive chemical kinetic models. So let's jump into the second section of this lecture and talk about agentic AI. We all know what AI is, but just to be formal, let's standardize the jargon and the definitions. So AI, artificial intelligence, that's the umbrella discipline. So it's in computer science. That's what we will call classical AI tasks like machine learning tools and so on. Machine learning, deep learning, and agents, everything fits into AI, of course. Next, we have generative AI, and that's what we know in the general public for generating images and text and code and audio and video. So we all know these tools, which came to our lives about 2.5 years ago and really took on acceleration in the past 1.5 years and do fantastic work. Next, we have AI agent. An AI agent is a system that's capable of perceiving automatically. So it could be a sensor in real life. It could be a software that identifies and that reads. So any perception, then it makes a decision. It has rationale in it, based usually on LLM, but it's also capable of actually performing an action. That action could be in the real world, like an autonomous car, and it could also be a software action that really matters in our workflow. So that's a definition of an agent, an autonomous system for one bounded task, perception, decision, and action. A higher level than an AI agent is agentic AI. So now we have a system of agents. Actually, we don't want too many agents, so we don't want it to be messy. We want the precise number of agents well-defined plus an orchestrator that manages all of them. And that's a difference between using just one agent, which is a linear task. Here we can do a cyclic and a complex framework of tasks that these agentic AI procedures and these agents can perform for us. And that's what we'll focus on for our chemical kinetic agentic AI. So these were just definitions. And next, we drew an analogy from a very known concept, a very known book by Daniel Kahneman and his late colleague Amos Tversky, Nobel Prize laureates, that came up with a few ideas which were later on summarized in this popular book, Thinking Fast and Slow. And they described the human brain as having two systems. They actually call it in this book System 1 and System 2. System one is what thinks fast. So it says you're unconscious. It's not that it doesn't have consciousness, but it thinks fast. It can make mistakes, as I'm doing right now. I'm speaking fast. It doesn't stop to think rationally. And really, we're grateful for having that system as well. If we're asked a math problem and we know the answer, we'll just draw it. But if we have to stop and think about it, it takes more effort, so we burn more ATP, it's slower, and it's logical. We take that analogy onto agentic AI, and we also divide our workflow into two systems. System one is the automation layer, and here it is. We've been working in our field for years now to develop this automation layer. Briefly, what it has is a model generation software, so we can think about that as RMG, the reaction mechanism generator that I just showed. Then selecting parameters that we want to improve using sensitivity analysis. Later on, computing them using ab initio method, so that's where ARC fits. And overall, we don't have to go into all the details here. Overall, we have a layer of automation that anyone can use to generate predictive chemical kinetic models. On top of that, we now have system two that we are building. So system two is where we do the thinking and the rationale. Classically, humans have done that, and we're not so thorough because, the joke is, when do you finish refining a model? When the PhD student has to graduate. But an AI agent can work faster, doesn't have to graduate, and the PhD students in our group are now using the agents to get models faster, and they're able to judge them, to evaluate them, because they also understand the material deeply. So what are the agents here, and what is this agentic level? Let's go into detail and explore it a bit. We have a planning agent first. So this planning agent will set goals for us and constraints. For example, we can tell it, set the objectives for us, determine the ignition delay time of sustainable aviation fuel mixture between these pressures and these temperatures, and it will decompose the objectives into actionable tasks. Next, we have a tool agent. So that means go and generate a model. So what's the tolerance? I mentioned that briefly when we saw RMG. Which parameters to use? RMG needs a bunch of parameters and we need someone to decide about that. And when we run quantum mechanical calculations, like in ARC, what DFT level do we use, for example? So that tool agent make these decisions exactly. And it's not free language, so it's less prone to make mistakes. It is typed and goes through a layer of verification before sending commands to the automation layer. We have an experimental design agent. That agent will break apart a big campaign into which orthogonal set of experiments, the minimal set of experiments we have to run in our lab, for example, to validate the model. So it will give us an output like that, for example. We have a revision agent that's currently in building, and here we want to mimic a chemist intuition that will look at the model and will tell us, hey guys, you're missing a few species, or how come you don't have that reaction? So now we're coding and we're teaching the computer to understand what it doesn't know. And that's a philosophical question, of course, but we have 30 questions, very wide, each one that necessitates more computations, sometimes more experiments to investigate what we're missing if the model indeed does not agree with the validation experiments. Speaking about experiments, we're actually doing the wet work as well. We're not all theoretical, and we have a reactor that's a plug flow reactor. It's a self-driving reactor, so Python controls the reactor in terms of the temperature, the pressure, monitoring the gases that go out, everything that goes in, the mass flow controllers, so that's all being done automatically. To summarize, That's the architecture that we're currently building for predictive chemical kinetics, where users can give input, we generate the model, refine them, we validate automatically, we revise when needed, and everything here is being controlled by agentic AI. All right, so this image is a bit utopic, but just for fun, of course. To summarize, we've seen how we generate predictive chemical kinetic models and how we refine them, and how agentic AI can play a significant role in predictive chemical kinetics. Thank you very much for listening. I'm available for any questions. My details are here, and have a very productive conference. Thank you.